The technical data presented in this film have been derived from preliminary reports. Therefore, any conclusions and recommendations drawn herein are tentative, since completion of evaluation for the final report is still underway. Red Wing was a 17-shot operation, the most ambitious ever conducted at the Eniwetok Proving Ground. 4 were fired on Ivan, an airdrop, 2 tower shots, and a ground surface burst. In the Sally Pearl Ruby complex, 4 others were fired, all tower shots. There were 2 barge shots in the lagoon off Flora, and 1 was fired in a large tank of water on Irene. The Eniwetok shots ranged in yield from less than 1 kiloton up to 1.9 megatons. At Bikini, there were 6 firings during Red Wing. The Cherokee airdrop off the island of Charlie, a surface shot, 3 barge shots off Dog, and a shallow water barge shot on the Charlie Dog Reef. Yields ranged from 380 kilotons to about 5 megatons. It was around these devices, all basically developmental in character with the exception of Cherokee, that the military effects effort was centered. There were 8 weapons effects programs consisting of 47 projects that were carried out by 18 different government agencies and laboratories. The Cherokee shot was included in the series to study basic military effects and fallout from a high-yield airburst over land. It also provided the first opportunity for the Air Force to test techniques for the delivery of a megaton weapon. The drop aircraft was a B-52. Height of burst was to be 5,000 feet, and 0 point was on the island of Charlie at Bikini Atoll. Blast studies in free air were concerned primarily with measurements of a high-yield airburst to document propagation of the blast wave through a non-homogeneous atmosphere. One technique used to obtain this data was to fire smoke rockets behind the 0 point to form a smoke grid, and then to photograph the shock propagation against this grid. A means of obtaining measurements of free air peak overpressures versus time vertically above a megaton yield airburst utilized an array of 12 parachute-borne telemetering blast pressure canisters dropped from a B-36. At shock arrival time, the canisters were to be in this position, ranging in altitude from 14,000 to 39,000 feet above the burst. The Cherokee weapon was detonated on 21 May 1956 with a yield of 3.8 megatons and a height of burst of 4,320 feet. This was the intended 0 point for Cherokee. This was the actual 0 point, some 19,000 feet to the northeast. Because of the bombing error, the blast program's effort to obtain basic blast data on a high-yield airburst was seriously affected. The free air measurements made by parachute-borne canisters were partially successful, since only low pressures were recorded at rather long horizontal ranges from the burst point, and the data could not be correlated with shock photography. Nevertheless, some basic data were obtained that will allow a limited evaluation of various scaling methods for correcting for the effects of atmospheric inhomogeneity. Analysis of these data is being made concurrently with similar information obtained by different methods on other events in the Red Wing series. Another of the multi-megaton devices fired at Bikini was Navajo. 0 point was a barge in the lagoon off Dog Island. Studies were made here to obtain further data on water waves created by the energy release from high-yield devices. Such water waves are considered to be created by 2 phenomena. First, in the immediate area of the burst, energy transfer in the form of initial impulse and fluid displacement produce the most significant waves. Secondly, at more distant ranges, up to hundreds of miles, waves are initiated by an air coupling mechanism which is still being studied. Navajo was fired with a yield of 4.8 megatons. 17 minutes after the detonation, the water wave had traveled a distance of 18 miles, and this is what occurred on the island of Nan. Stop-motion photography recorded a wave some 11 feet in height as it swept across the island. On the island of Yvonne at Eniwetok Atoll, other blast studies were carried out. On a 40-kiloton surface burst, 10 jeeps were located facing into and broadside to the blast at distances ranging from 2,500 to 4,380 feet from 0 point. This and similar exposures on other shots were continuations of statistical studies from Upshot Knothole, Castle, and Teapot to assist in making damage prediction charts for TM-23-200 so as to provide added reliability for damage prediction to all types of military vehicles. Preliminary analysis of the data collected from jeeps indicates that a good correlation was achieved with the existing damage prediction charts for TM-23-200. Also on Yvonne, stations were set up to record drag force measurements on a 40-kiloton surface burst. Cubes, parallelepipeds, cylinders, and spheres were placed at 2,500 and 5,000 feet from ground zero and instrumented to check the correlation of field tests with wind tunnel and shock tube laboratory tests. Drag force data were obtained, which will allow comparison with the field results of Operation Teapot and which can be correlated with identical scale models tested under laboratory conditions in the shock tube. Another objective of the blast and shock studies was to ascertain and investigate the existence of precursor waves resulting from surface firings and to observe the difference in these effects over vegetated and sandy surfaces in a strong precursor region from a tower shot. The vegetation consisted of vines, grass, and broadleaf shrubs 10 to 15 feet high. In comparing findings from the cleared and uncleared areas, it was found that the vegetation had a suppressing effect on precursor formation and propagation as compared to that over a cleared area. It is believed that wet soil conditions and high thermal energy attenuation in the air of the Eniwetok Proving Ground adversely affected precursor formation, since precursors at the Eniwetok Proving Ground were weaker than those over the dry soil in the clear air of Nevada. Precursor-type waveforms were recorded on both surface events. In addition, a good range of crater data was obtained under a wide range of conditions and environments. For example, La Crosse was fired on the reef with a yield of 39.5 kilotons, and the crater was 404 feet in diameter, 44 feet deep, and had a 15-foot classical crater lip. Zuni was fired at Bikini on an island with a yield of 3.5 megatons. This crater had a diameter of 2,310 feet, was 103 feet deep, and had a 15-foot irregular crater lip. Such data will increase the reliability of crater predictions. The structures effort was chiefly concerned with checking the effect of the relatively long duration of the positive phase of the megaton blast wave on structural responses. During Teapot, the response to blasts of short-duration positive phase was studied. There were many unresolved questions concerning the applicability of a simplified mathematical model to the load duration problem. On Teapot, the responses of 4 typical single-story steel frame industrial buildings to a 22-kiloton burst with a relatively short-duration positive blast phase were documented. The Red Wing, or second part of this study, was made to record the responses of identical industrial buildings to a large yield detonation having a relatively long duration positive blast phase. An airburst with a predicted yield of 4.5 megatons was selected for this test. There were 6 steel frame buildings. The three drag-type structures were 30 feet high, 40 feet in span, and 40 feet long. The three semi-drag-type structures had the same height and span, but were 80 feet long. The 6 buildings were located on 3 man-made islands on the shallow water reef between the islands of Charlie and Dog and on the island of Dog, at ranges of 20,500, 24,000, 29,000, and 35,600 feet from the intended air zero, and placed so that the range and damage would be as great as possible. They were instrumented to obtain transient structural deflections, strains, and accelerations, as well as overpressure versus time and dynamic pressure versus time relationships. At shot time, high-speed remote cameras trained on the structures recorded arrival of the thermal radiation. It was also intended for the cameras to record arrival of the shock front, but they ceased operation prior to that time. Although the actual yield was only 3.8 megatons, the 19,000-foot bombing error to the northeast of intended Cherokee Zero caused all structures to be subjected to pressures higher than expected, and the planned gradation of damages was not achieved since all buildings collapsed. As a result, less data than expected was obtained on drag and semi-drag type buildings. Nevertheless, a comparison of the identical structures tested during Teapot and Red Wing indicates that the most important result was a full qualitative demonstration of the greater effectiveness of the long-duration blast wave associated with megaton yield weapons. The thermal radiation and effects program had a primary objective of documenting the thermal phenomenology associated with the multi-megaton air bursts. A secondary objective covered the collection of data on thermal phenomena and thermal effects on materials. The target miss on Cherokee seriously compromised the realization of the primary program objective, but additional data were recorded on thermal phenomena and thermal effects on materials. Studies of the effects of nuclear weapons on aircraft in flight, conducted previously during operations Greenhouse, Ivy, Upshot Knothole, Castle, and Teapot, were continued. Previous tests indicated the critical importance of thermal effects on aircraft structures with respect to subsequent loading of the heated structure by both gust and overpressure. During Red Wing, 6 Air Force aircraft, the B-47, B-52, B-66, B-57, F-84, and F-101, and 1 Navy aircraft, the A-3D-1, were primarily concerned with determination of delivery capabilities. Each plane carried a maximum amount of instrumentation, calorimeters, radiometers, and thermocouples for thermal input and response measurements. Transducers and strain gauges to record shear, bending, and torsion of the wing, tail, and fuselage surfaces. Other instrumentation included gyros to measure angles of roll and pitch, pressure transducers to record overpressures, accelerometers for measurement of structural accelerations, plus oscillographs and cameras to record aircraft positioning information, wing deflections, and other data. In the early morning before 0 hour, the effects aircraft took off from Eniwetok and headed for their shot time orbits. To position the aircraft at precise locations in space, and to have a complete record of the flight paths at zero time and at time of shock arrival, various aircraft and ground electronic positioning systems were used. An important factor in the positioning of aircraft was the uncertainty of predictable yields for the experimental devices being fired. In general, gust response limits were set at 100% or less of limit load. Thermal effect responses were restricted to total temperature in thin skins of approximately 500 degrees Fahrenheit, and radiation dosage was limited to a 3.9 Roentgen total. Therefore, a positioning yield somewhat higher than the design yield was used in positioning the aircraft to provide a safety factor because of the unknowns of weapon performance. For example, with the Zuni device, the predicted yield was 1 to 3 megatons. The safety factor stated that aircraft positioning yield would be 5 megatons. The actual yield of this device was 3.5 megatons. Back on the ground following each mission, data reduction of aircraft effects began. The objectives of the aircraft effects program were fully met during this operation. A definite conservatism in the prediction methods for thermal inputs was noted, with predicted values being significantly higher than measured values. The results will be useful in developing more precise methods for prediction of thermal input and response parameters. Additionally, a conservatism was noted in the prediction methods of total dosage from nuclear radiation. Air crews received about half of the predicted doses. The importance of being able to predict radiation fields with resultant dosages to crews in the delivery of lower yield kiloton range weapons by high-speed fighter-type aircraft becomes paramount. As to blast effects, it was noted that the bomb bay doors and forward wheel well doors of the B-47 were moderately damaged at 0.84 psi on one shot. The B-52 bomb bay doors and various aerodynamic seals were damaged by both the thermal input and an overpressure of 0.87 psi on one shot. The B-47 and B-57 both sustained wrinkled control surfaces and tabs because of high thermal inputs. And the honeycomb skin of the F-101 was a thermal limiting item, with the skin on the stabilator and wing becoming unbonded with a temperature rise of about 450 degrees Fahrenheit. Such findings should be reflected in the design of future aircraft and the modification of existing models. During the Red Wing missions, neither gust effects on engines nor overpressures and thermal effects on the various aircraft components created adverse control or performance problems. Delivery capabilities were proven out in all instances. Further testing of these aircraft to satisfy the Red Wing objectives will be unnecessary. The biomedical effects program consisted of one project with the objective of obtaining information on the requirements for protection against chorioretinal burns. Rabbits and monkeys were exposed to the thermal pulse of several Red Wing detonations. Timing and shutter mechanisms for fractionating the light pulse time-wise, and shutters and filters as possible protective devices for the eye were tested at all stations. The animals were exposed on 11 of the Red Wing shots. And results indicate that climatic conditions and the thermal pulse characteristics at some exposure stations reduced the radiant exposure below the threshold necessary to produce chorioretinal burns. Both the first and second peak irradiances may produce chorioretinal burns, and the blink reflex is not fast enough to protect the eye. Data obtained should be of value in the development of eye protective devices. Another of the Red Wing effect studies was concerned with the long-range detection of nuclear detonations by utilizing the electromagnetic pulse radiated by the detonation. This project had its major activity outside the Eniwetok Proving Ground. A network of distant stations from the eastern United States to Hawaii and the western Pacific were set up to detect the pulse from the detonations and study its characteristics. It was successfully demonstrated that operationally usable lines of position and fixes could be obtained from the bomb pulse at great distances. Distinguishing the bomb pulse from spherics, pulses from lightning and other natural sources still present some problems. Aerial photographic techniques were used to make photogrammetric determinations of various parameters of nuclear clouds as a function of time, and to attempt to establish approximate scaling yield relations. Excellent navigation, together with improved camera installations, made it possible to obtain more complete cloud survey data than on any previous operation. The nature and distribution of radioactive fallout from high-yield thermonuclear detonations was one of the prime objectives of the Red Wing operation. It was an integrated program which included land, sea, and air stations to collect data during and after the fallout event. To measure the activity distribution within the nuclear mushroom, single-stage rockets were mounted and aimed to pass through both cloud and stem. The rockets, carrying detection units with telemetering transmitters, were fired into the stem and cloud at H+7 and H+15 minutes. The telemetered radiation exposure rate was then recorded on magnetic tapes in island and shipboard recording stations. To study the physical, chemical, and radiochemical nature of fallout after it reaches the surface, a number of collection techniques were used. Land stations located throughout the atoll consisted of total and time incremental collection devices for the purpose of gathering gross samples as well as samples versus time, from which time of arrival, rate of fallout, and time of cessation could be established. Since available land areas were covered by only a small fraction of the total fallout pattern, an array of floating instrument stations was moored within the lagoon and at sea to the north of the atoll. 3 pontoon rafts, instrumented to measure time of arrival, total exposure, and to collect total fallout samples, were moored in the lagoon. In addition, 2 YFNB barges with total and time incremental samplers and a variety of other instrumentation were moored inside the lagoon. In the ocean to the north of the atoll, some 16 skiffs were moored to collect total fallout samples, measure integrated exposure, time of arrival, and penetration of activity to various ocean depths. There were 3 fallout ships, YAG-39, YAG-40, and the LST-611, which were moved into position in the expected fallout zone prior to arrival of fallout to permit collection of total and incremental fallout samples at critical locations within the predicted pattern, as well as to make determinations of time of arrival, rate of arrival, cessation, particle size distribution with time, and other pertinent fallout parameters. The YAG-40 was outfitted with a special laboratory where early time studies of the collected fallout material were performed. Panels of typical building materials and common shipboard items were placed aboard the 3 ships for contamination-decontamination studies. In addition, masonite phantoms were exposed in a project to evaluate the performance of certain Navy dosimeters. The ships were also instrumented to measure the shielding effectiveness of various thicknesses of steel as a function of time, and to determine the gamma radiation fields produced by the ship's surface, air envelope, and water distribution of fallout contaminant, as well as serving to evaluate the effectiveness of washdown systems during fallout. The contaminated ships were utilized to test various decontamination procedures after their return to Eniwetok. To document the resulting fallout patterns, both aerial and sea surface surveys were carried out. P-2V aircraft, instrumented with very sensitive radiation detectors, were flown over the contaminated ocean areas to give an early definition of the pattern. This instrumentation was also used for making air absorption measurements, which permitted air survey data to be related to the exposure rates that existed 3 feet above the ocean surface. The surface surveys were accomplished by 2 destroyer escorts and the oceanographic survey vessel Horizon. Guided by the information resulting from the early aerial surveys, these ships moved into the ocean areas after fallout had been deposited to make exposure rate measurements just below the ocean surface. Periodic measurements of exposure rate versus depth, and to take water samples for analysis. This coordination of effort was made possible through the unified direction of the fallout program from a central control center. This Program 2 control center was located aboard the Joint Task Force flagship, the USS Estes. From here, communications were maintained with all elements of the fallout program. The YAGs and LST were positioned prior to fallout arrival based on predictions. The aircraft surveys were initiated and controlled, and the ocean surveys were directed, all under the supervision of the senior scientific personnel centrally located at the control center. In this way, an integrated effort of many separate elements was achieved, thereby resulting in a thorough documentation of the resultant patterns. To provide additional information on early cloud penetration and to permit determination of exposure and exposure rates encountered in flying through clouds produced by megaton range detonations, a number of B-57B aircraft equipped with appropriate instrumentation were flown through the stem and cloud base at times as early as 20 minutes after detonation. The data obtained is also valuable in determining the spatial distribution of the activity within the mushroom. During Red Wing, all types of firings, air bursts, land surface bursts, and water surface bursts were documented to obtain the maximum amount of information on fallout phenomena. On all types, the concentration of activity in the stabilized cloud seemed to be more dense in the layers near the bottom of the cloud. The stem activity concentration appeared to be less than 3% of that in the cloud. The ocean and aerial surveys, in conjunction with the data from collector stations, permitted construction of fallout patterns from the contaminating shots. The Cherokee shot, intended as a megaton airburst over land, actually showed that an airburst over water does not produce downwind fallout areas of military significance. Whether or not this is the case over land remains to be determined. The land surface and water surface bursts did produce tremendous areas in which exposed personnel would receive lethal dosages. This data should be helpful in the construction of fallout models from which prediction methods could be developed. The data from Red Wing confirmed the Castle finding of the significant extent of hazardous radioactive fallout resulting from the surface detonations of high-yield weapons. The results of the 8 weapons effects programs conducted during the 17-shot Red Wing operation were many and covered a wide range of data. Because of the magnitude, it is possible to summarize only a few. The blast and shock program was successful in meeting its objectives, except for the loss of data on Cherokee. Aircraft effects tests proved out delivery capabilities in all instances, and Red Wing objectives were fully accomplished. A comparison of the identical Red Wing and teapot structures provided a full-scale qualitative demonstration of the effectiveness of the long-duration blast wave associated with megaton-yield weapons. The results confirmed on a full-scale basis theoretical studies which have indicated that as the length of the positive phase of the blast wave increases, the overpressure required to cause a given degree of damage decreases. The fallout studies of megaton-yield surface bursts during Red Wing showed that the fallout hazard can be of military significance over areas of several thousand square miles. On all shots during Red Wing, a high percentage of the instrumentation functioned properly and resulted in varying degrees of success in the documentation of megaton and kiloton effects. This documentation modified existing data, extended presently established theories, and added to the knowledge of phenomena in areas heretofore only partially documented.